This is a video supplementary for understanding the latent manifold dynamics under iterative feedback processes. What is a latent manifold distribution? Latent manifold distribution is the representation of features inside a neural space. Under iterative feedback processes, this distribution is affected at two levels. First, at the local level, which is at the class distribution level, and second, at the global level, which is at the data distribution level. Suppose this is the baseline distribution of a data. This data under iterative feedback processes can expand, where the features will spread out, and it can contract, where the features will shrink in. To measure these changes, we use three different metrics. First is intra-class spread, which is the average feature spread per class. Second is the MLE-based local dimension estimation method, which we call intrinsic dimensions. The third one measures the global dimension by using the full eigenvalue spectrum of the whole distribution. Let's see how the local and the global dimensions behave in a twice setting. Suppose the bigger sphere represents the global dimension of a data distribution and the smaller sphere represents local dimension of a class. Starting with all the three classes in a 3D sphere form, we see that the local dimension for each class is around 3.5 and the global dimension for whole data distribution is 1.91. Suppose we flatten one of the class to a disk shape. The corresponding dimension reduces to 2.46 and the global dimension reduces to 1.85. Similarly, if we flatten two class distributions into a disk shape, the global dimension reduces to 1.77. And when we flatten all the class distribution to disk shape, the global dimension reduces to 1.70. Keeping that in mind, now let's look at the proposed 8-dimensional patterns. Based on the behavior of intra-class spread, we divide the patterns into two parts. First, the semantic expansion regime, where the intra-class spread increases. Second, the semantic contraction regime, where the intra-class spread decreases. Pitching the global and the local dimensional metric behavior against the intra-class spread metric, we get 4 pairs of dimensional patterns. First is coherent expansion. In coherent expansion, both the local and the global dimensions increase, like an inflating balloon expanding locally and globally. Coherent contraction is the reverse of that behavior. Second is wrinkled expansion. In wrinkled expansion, the local dimensions increase, but the global dimensions decrease. Wrinkles or folds are formed within the class distribution, increasing the local dimensions. Anisotropic contraction is the reverse of this behavior. Third is anisotropic expansion. In this, the local dimensions decrease, but the global dimensions increase. It is like a Play-Doh being stretched, decreasing locally but increasing global dimensions. Wrinkle contraction is the reverse of this behavior. The final one is the oblate expansion, in which both the local and the global dimensions decrease. It is like a balloon being squeezed between two plates, collapsing both dimensions. Oblate contraction is the reverse of this behavior. Now we will look at the animation of each pair of patterns. Let's start with coherent expansion and contraction. This animation starts with 3 2D class distribution which is expanding outward like a balloon. the local dimension and the global dimension increase together, expanding the overall dimension. The reverse of this behavior represents coherent contraction. Now let's observe the oblate expansion and contraction process. The animation starts with 3D class distribution, which is slowly spreading only along few directions and collapsing along other directions, like flattening from a 3D sphere into a 2D disk, but also spreading out in the process, just like squeezing a balloon between two plates. In this case, both local and the global dimensions move together. Now let's observe the wrinkle contraction and anisotropic expansion. The animation starts with anisotropic distribution of class features, which is contracting with folds or wrinkles. Wrinkles are formed locally to convert the anisotropic spread into 3D spheres. In this case, while the local dimensions increase because of wrinkles, the global dimensions decrease. Now let's observe the final pair of wrinkled expansion and anisotropic contraction. The class distribution starts as a thin, elongated anisotropic distribution which is expanding locally because of wrinkle formation. The local dimensions increase, but the global dimensions decrease. The effect of global decrease suddenly shows up later in the animation.